I would like you to look at this cartoon.
Oh, the large house plus I get it. I get it.
What is the antiderivative of 1 over x, Trevor?
Oh, natural law. Oh.
Uh-huh. So 1 over house is now log cabin. So, or we can say cabin become log cabin.
Yeah.
Okay. What?
We have that joke for our worksheet. We have that.
Oh, yeah. So you okay. So we really looked at specific examples yesterday that involved power rule and trigonometry. Okay, well we know more anti-differentiation rules than that. We know natural log and exponential functions. Okay, that's what our focus is going to be today. So sometimes our denominator as a whole can be a perfect candidate for U substitution. Do you notice here how the denominator is 1 degree higher, polynomial, than the numerator? Okay, that should kind of be like a warning sign to you that maybe U substitution is going to be able to work out. If we let our denominator equal U, then du is 2x dx. Well, look at that. There's x dx. Okay. So this means our antiderivative becomes 1/2 1 over u du. Okay, the antiderivative would then be 1/2 natural log of the absolute value of u. And then we can replace u again. Now, is it necessary that I put the absolute value in this particular answer? It's not. X squared plus 1 is always going to be positive, so it's actually kind of redundant that we have the absolute value there, but I will never get upset for you having the absolute value in the antiderivative when it's a logarithmic answer, okay? I don't care if it's redundant. If you put it there, I'm totally cool, but if you see that you don't need it, I'm also okay with that too, okay? What I don't want is for you to get in a habit and then not put it where it is needed. Next example. Okay, so these past two examples, the composition might not be as obvious because to us it just looks like a fraction, right? Well, our composition is we have a function in the 1 over x function, which doesn't always like ring a bell to us maybe, but you still need to be able to look for that. So what do you notice about this fraction? What? Okay, the numerator has a higher power. What else do you notice? The derivative of tangent is secant squared. That's nice, right? Which means if we let u equal the tangent of x, then du is secant squared x dx. Okay, so Michael was actually good that it was a higher power, right? Because it has this relationship. All right, so our antiderivative, our integral becomes, quite simply, 1 over u du. So we have the natural log of the absolute value of the tangent of x plus c. Okay, I'm going to put another example up here. As you write it down, I want you to brainstorm with your pod what we're going to do with it. How are we going to solve it? We'll make it big. Okay, but specific. Specific to u substitution.
I think,
All right, I hear some good conversations. Does anybody want to offer up some advice for the class? I heard like 3 pods talking about it.
I think we should make u equal the natural log of x.
And if u equals the natural log of x, du would be what? 1 over x dx? Is that helpful? Okay, when you see it, it's like obvious, right? But when you don't see it, it's frustrating, okay? We just gotta go through these examples to get some ideas of different things that we can do. So u is the natural log of x, it's in our denominator, right? The derivative is 1 over x dx. Well, we have that right here. We have 1 over x dx. So we can write this now as the integral of 1 over u du. Now this is a little bit awkward, right? Okay. The antiderivative would then be the natural log of the absolute value of u plus c. So our answer is the natural log of the natural log of x plus c. Awkward? Okay. Maybe you're a little nervous about this answer. What could you do? We could take the derivative. If we take the derivative of the natural log of the natural log of x, let's see. Remember how we do that? Well, we do the chain rule, right? 1 over what's inside times the derivative of what's inside. There we go. That's what we started with. Our antiderivative is okay. The time has come. We finally have a way to figure out what the antiderivative of tangent is. Has it bothered anybody that we haven't talked about it? Not really. Okay. Hasn't even crossed your mind. Glad you weren't worried. We don't have just a simple rule for the tangent of x. We will have today, but what would be helpful? How could we rewrite the tangent of x so that we could maybe do something with it to find the antiderivative? I think that we can rewrite it either way, but since we don't have a simple rule for cotangent, that's probably not going to be the one that's helpful. But we have rules for sine and cosine, right? Okay, now, we can't just take the derivative of sine divided by cosine, but we do have this technique called u substitution, and we have a composition here, okay? Now, be thoughtful. Which one do we pick for our u?
Cosine.
Yes, ready for that. Because our du is sine x, that's in the numerator. We need to have sine x times dx, so it has to be our numerator. Good call. Thank you for paying attention. I just am getting so excited about this. Okay. So what we have is negative the integral of 1 over u du. And some of you can even write the answer from here, right? But we'll go step by step. Negative natural log of the absolute value of u plus c. So the antiderivative for tangent is negative natural log of the absolute value of cosine plus c. We got one. I would like you to take the next 2 minutes and determine what the antiderivative of cotangent is, please. Well, be careful with the word opposite.
Well,
Is the answer going to be similar? Yes. Figure out what it's going to be. I don't think that's going to help though. Okay, Will, what'd you get? Yep.
Natural log of the absolute value of sine of x plus c.
Trevor? Kind of opposite, not
oh,
quite.
yeah.
Yeah. So one's positive, one's negative, one has sine, one has cosine, but they are very similar in their appearance. We have 2 more questions, or 2 more examples to go through, and then I'm going to give you a task at your table. Okay? Okay. Thoughts on this one? Yeah. The polynomial in the numerator is higher than the denominator. Now, when we did our very first example, I got really excited because the denominator had a higher degree, right? We made the denominator u, and then that was helpful with our numerator. That is not the case here, right? If our numerator is bigger, what kind of fraction do we have? Five fourths, 10 halves. We have an improper fraction, and what can we do with improper fractions? We can rewrite that as by doing what? We can take the numerator and divide it by the denominator. What?
I forget.
This is why we're going to go through this. Once we go through it once and we're like, oh yeah, this isn't that bad. You did it in Algebra 2, you did it in pre-calculus, we can do it in calculus. All right. X times what is 2x squared? 2x. Then you take x times 2x, negative 2 times 2x. And what do you do with these numbers? We subtract them. And then we repeat. X times what is 3x? 3. We multiply x minus 2 to 3. And subtract. No one's going to stop me, were they? Where's my mistake?
Oh, yes.
I have add, but what did I do? What should this be? 11x minus 3. Get a remainder of 19. Doesn't matter what the remainder is. I mean, it does, but doesn't matter how big it is. So now, instead of that improper fraction, we can write 2x plus 11 plus our remainder over the divisor. And I'll scoop this up here. Our quotient is 2x plus 11, and then we tack on our remainder over the divisor. Now this is nice. What's the what? Oh, I thought you, okay. It is good time. Thank you, Eli. What is the antiderivative of 2x? Antiderivative of 11. 11x. And then we have a linear denominator. We don't have to do u substitution for this. We know it's going to be 19 times the natural log of x, absolute value of x minus 2. All right, that one was kind of crazy. Kind of threw you for a loop there. Let's go back to something a little bit more calm. But a function we haven't dealt a lot with this semester. E to the x. All right. So this is one where, yeah, we probably could multiply it all out to do our antiderivative term by term. Or we have a nice composition where we could let u equal what? E to the x plus 1, because that's inside a squared function. Du is du to the x dx. We have e to the x dx. So this becomes integral of u squared du. Okay?